let's explore some more representations of lists. Specifically, I'd like to talk about two especially useful ones. First of all, a nice syntactic sugar for lists, and second of all, a really interesting graphical representation for lists. So a list is either an empty list written as nil or an element followed by a vertical bar followed by another list. So that's one way of writing a list. In fact, that way corresponds closely to the semantic definition. But we've already seen another way, the bracket notation. So let me take the list 10, 11, 12 and write it in bracket notation. It's a vertical bracket, 10, 11, 12 with spaces, and another vertical bracket to terminate. So the same list, in fact, is written in two different ways. Okay, these two different ways of writing lists change nothing about how the list is represented in the system. It's purely something convenient for the programmers. So a convenience that provides different syntaxes that are more easy to use for programmers are called syntactic sugar. And the bracket notation we saw is an example of syntactic sugar. But I have to emphasize that inside of the system's memory, the two lists 10 bar 11 bar 12 bar nil and bracket 10 11 12 bracket are exactly the same. And I can verify this by comparing them. So I do a browse, I do 10 bar 11 bar 12 bar nil equal 10 11 12. I execute this and the system replies true. For the system, there is no difference between these two. The second representation of a list that I'd like to talk about is a graphical representation as a binary tree. So a tree is a kind of graph, a figure with nodes and edges, which are lines connecting the nodes. In a tree, one of the nodes is special. It's called the root of the tree. If that's all we have, just this one node, then the tree is empty, the smallest possible tree, and we always also can call it a leaf. You note the botanical inspiration of the idea. Otherwise, the root might have several edges leaving it, going to other trees, and these are called subtrees. If there are always exactly two edges leaving each root, then we have a binary tree. You note actually that this is a recursive definition, similar in style to the recursive definition of a list. In fact, trees are just as recursive as lists, and let me bring in a diagram to explain it. So a tree, so here's an example of a tree. So a tree is either a leaf node, a single node, which is an empty tree, or a root node with arrows to a set of trees, subtrees. In this particular diagram, there are two subtrees of this R root. And a binary tree is a tree where all root nodes have exactly two subtrees, one of which is called the left and the other one which is called the right subtree. Okay, so I'm not going to go further into studying trees as such, although later on we will have a lesson that's focused on trees, but I will show how lists are a form of tree. So for example, let me bring in a diagram. Given the list 10 bar, 11 bar, 12 bar nil, we take the first bar and we consider it the root of the tree here. And then we take the element, the first element of the list, and it becomes the left subtree. And we take the rest of the list, so the recursive part of the list, and this becomes the right subtree. So we have then here a vertical bar as the root, 10 as the left subtree. The right subtree is another vertical bar as a root with 11 as subtree. The right, again, is a vertical bar. Left is 12, and the right is nil. So there's always a kind of backbone here of vertical bars ending in nil. And that's a graphical representation of a list as a particular kind of binary tree. So personally, I like this kind of representation very much. I'm a visual person. I like to reason on diagrams. And if you're like that, you will like it too. It's especially an enlightening definition if you have nested lists. Lists whose elements are lists. So let me give you an example. Take the following list. A bar nil with parentheses bar, B bar nil, parentheses bar nil. So, draw a picture of this. Or here's another example. A bar B, in parentheses, bar, C bar D, in parentheses, nil. So the first question for this second one, is it a list? And the second question, is the left subtree a list? Does it follow the definition of lists? And if you have understood the graphical representation, you can see at a glance whether it's a list or not.